Hello and welcome to lab number 4. Now what we're going to do here is we're going to follow up on some questions that came up that we developed when we were doing lab number 3. In lab number 3 we established the idea of force being a push or a pull. We established how we can measure force using newtons in SI. And we also saw that there was a relationship between force and acceleration. Namely that if you increase a force applied to an object, it increases the acceleration in a linear fashion. And it seems to be that the constant of proportionality is the mass of the cart, the mass of the object being accelerated. In our experiments in lab number 3, what we did was we applied force in the same direction of the motion. That is to say, we had the cart being pulled in the positive direction and we saw that it had a positive acceleration. What happens if we apply the force in the opposite direction? That is to say, well, what we have right now, for example. On page 87, there's a setup where you have the cart being, well, let me describe it here. We have our motion sensor here on screen right, and we have our cart here, and the cart is lined up to go from, on screen left, and it's supposed to move from left to right on your screen. Since the motion sensor is on the left, since the motion sensor is on the right, then moving in this direction is positive velocity. And this direction is the positive direction, and this direction is the negative direction. Since we have our weight hanging on this side where the motion sensor is, the force is going to be applied in the negative direction. So let's go ahead and do prediction 1-1. Suppose that you give the cart a push toward the right and release it. Draw below vectors that might represent the velocity, force, and acceleration of the cart at each time after it is released and is moving toward the right. Be sure to mark your arrows with F, V, or A as appropriate. Assume that the cart is moving towards the right at time 1 and at time 4. And on your sketch there, on the diagram, you see that the distance that the cart travels as it goes from left to right is getting smaller each time. So our velocity looks like it's pointing into the positive x direction, but what's the direction of the change in velocity? And of course, the way we have the cart set up, the way we have the force set up, the force is pointed in the negative direction. So make your prediction. If the positive x direction is toward the right, what are the signs of the velocity, the force, and acceleration after the cart is released and moving towards the right? And what we see is the velocity should be positive, the force should be negative. Question for you is, what's the sign of the acceleration going to be? Now let's go ahead and test the prediction. I've got it already set up. I've got 30 grams hanging over here that's going to drive the system. And the way I'm going to move the system is I'm going to start here, give the cart a push. The cart will move along to a certain point, eventually come to a stop, and that's where we'll stop the recording. When we're done, on page 88, you go ahead and sketch the graphs, and then we'll answer the questions that come along. So let me go ahead and first take the slack off the string, zero the force sensor so it reads accurately, and then reset it. And I will go ahead and start the recording. Okay, that seems to happen a lot. I've done this experiment a couple of times. The first run always seems to do that. Let's go here. And all right, as you can see, it stopped. So let's take a look at the signs of our properties. First, we'll look at the velocity, and I will scale that up. And as you can see, the velocity seems to be positive and decreasing. The force, we can read right away, the force is negative and constant. And what about the acceleration? Well, when I zoom in, we see that the acceleration is negative and constant as well. In fact, we could actually do a calculation here by using the mean. And the mean says that the acceleration is, wait a minute. Oh, I'm sorry. We got a spurious acceleration here. The acceleration is negative 0.5 meters per second, whereas the slope of the line gives us negative 0.53, which is consistent there. So we're in good shape for those pieces of information. So as I said before, go ahead and make your sketches. And we'll go ahead and answer the questions. Question 1-1, did the signs of the velocity, force, and acceleration agree with your predictions? If not, can you now explain the signs? Question 1-2, did the velocity and the acceleration both have the same sign? And we can see, yes, they indeed did have the same sign. Explain these signs based on the relationship between acceleration and velocity. Simply put, as the velocity is in the positive direction, it becomes less positive over time. That means that the acceleration had to be in the opposite direction. The acceleration had to be negative. In fact, if I do a motion diagram, essentially what we have is the velocity goes in this direction, there's v1. The next velocity is in that direction, there's v2. So therefore, there is the change in velocity, delta v, which gives us our acceleration in the opposite direction. Question 1-3, did the force and acceleration have the same sign? Yes, they did. Were the force and acceleration in the same direction? Yes, they were. Question 1-4, based on your observations, draw below the vectors that might represent the velocity, force, and acceleration of the cart at the same instant in time. And so you should be drawing a positive vector for velocity, but negative vectors for force and acceleration. And question 1-5, after you release the cart, was the force applied by the hanging mass constant, increasing, or decreasing? And explain why this force is necessary, why this type of force is necessary. We saw in Lab 3 that as you changed the mass, the acceleration changed. So if we had a constant force, we would expect to see a constant acceleration. Okay, so now let's do the next step, activity 1-2. What happens if it speeds up towards the motion detector? So what I'm going to do is I'm going to change the recording conditions a little bit. So the start condition is now going to be when it falls below 0.9 meters per second, 0.9 meters. Make that 1 meter. We'll test it to check. And then the stop condition is when the position falls below 0.20. Oh no, it's 0.25. Okay. So let's just check. We're just going to do a quick run here to check our start and stop conditions. I'll hit record. It's not recording. I release it. And it stopped recording when I wanted to. So let me go ahead and delete that run. And let's go ahead. Prediction 1-2. Suppose that you release the cart from rest and then move toward the motion detector. Draw on the diagram below the vectors that might represent the velocity, force, and acceleration of the cart at each time after it is released and moving towards the left. So as you can see now, the motion is going from the right to the left, so your velocity arrow should be to the left. It's speeding up, so your acceleration arrow should also be to the left. And the motion detector is where the force is being applied, so it looks like we should have a negative force. Let's test the prediction. So sketch on page 88 the results of this graph and use dashed lines so you don't get them mixed up. Okay, so again, I'm going to zero the force sensor so we can get an accurate force reading. Pull this out to the starting position and start recording. All right, and there's the recording there. And it looks like, for the most part, the acceleration is constant, the force is constant, and the velocity is constant. Excuse me. Or not the velocity is constant. The velocity is actually changing, but it's changing at a constant rate. Okay, so this is not a constant velocity, but it's a changing velocity, but each change along the way is the same. Okay, so does this agree with your predictions? If not, can you now explain the directions of the vectors? I'm sorry, question 1-6. Which of the signs, velocity, force, and or acceleration, are the same as in the previous activity? As we saw, the acceleration is the same and the force is the same. What's different is the velocity. So that's a big difference there. It seems that acceleration and force are tied together. Question 1-7, based on your observations, draw below vectors that might represent the force, velocity, and acceleration. All of them are going to be negative. Question 1-8, write down a simple rule that describes the relationship between the direction of the applied force and the direction of the acceleration for any motion of the cart. Well, in Lab 3, we gave it a positive force, so we got a positive acceleration. Here in Lab 4, we're applying a negative force, and we're getting a negative acceleration. So it seems that the signs of the force and the acceleration have to be the same. And question 1-9, is the direction of the velocity always the same as the direction of the force? Obviously, no. In the first experiment, the velocity was opposite the force. Instead, it slowed down. Now the velocity is in the direction of the force, the velocity speeds up, or the speed increases. Is the direction of the acceleration always the same as the direction of the force? Definitely. And last, in terms of magnitude and direction, what is the effect of a force on the motion of an object? It seems to be that if we apply a force, the object will accelerate in the direction of the force. Okay? Now we're going to do one more experiment, and in order to do that, I've got to change the recording conditions one more time. I'm going to change the start condition so that when it rises, so we're going to start when it rises above 0.25 meters, and it's going to stop recording when it comes back and hits the bumper. This will give us extension 1-3, reversing the direction. We're going to do the same thing. What we're going to do is we're going to start here, give it a push, let it come to a momentary stop, and come back all the way. What's the velocity graph going to look like? What's the force graph going to look like? What's the acceleration graph going to look like? Okay. I'm going to go ahead and let me do a quick change here. I'm going to change this to acceleration and this to force so that it matches the sketch, or excuse me, so that it matches the axes on page 91. Okay, so there's the force, and here's the acceleration. Okay, so let's go ahead and do the experiment. Zero the force sensor, put the load back on, start recording. Okay, we're going to try this again. Obviously that didn't work out. Let's try it one more time. Okay, now let's take a look at what the graphs look like. For the velocity graph, we see, no surprise, an initial positive velocity, momentary zero, negative velocity. For the acceleration graph, we see a constant negative acceleration. And for the force graph, we see that we had a constant negative force. So question 110. Compare your observations with your predictions. Describe the force and acceleration at the moment the cart reverses direction. Does the cart have acceleration at where the object is momentarily stopped? And the answer is yes, it does. It continues to have a negative acceleration. Based on your knowledge of the acceleration and force, explain why the force and acceleration have signs they have at the moment the cart reverses direction. The answer is, since the force is negative, the acceleration has to be negative. Okay, that finishes up investigation 1. So we'll go ahead and I will reset and set up, and we'll do investigation 2. Thank you very much.